Okay, folks, welcome to section 11.5, and it's a special section. It's the alternating series, which means that we're now going to investigate series that have some negative numbers, but in a very special way. I'm going to give you a very simple alternating series. Whoops, don't want to use S. A sub n is minus 1 to the n over n. So let's see, a1 minus 1 over 1, a2 plus 1 over 2, a3 minus 1 over 3, etc. Now, a lot of people like their alternating series to start with a positive number, and we'll see that in the proof actually makes use of that. So I'm going to make this another alternating series, but I'm going to change the exponent. A sub n equals minus 1 to the n plus 1 over n. Well, what's that do? Well, when we put in 1, we're going to get 1 plus 1 is 2, so we're going to get plus 1 over 1. And then when I put in a2, I'm going to get minus 1 to the cubed, so I'll get a2 is minus 1 over 2. a3 is plus 1 over 3. So it changed the sign of the series. These are all related, and any alternating series that has one plus or minus, you can just take off the first term and say this is a plus minus alternating series. So now what's interesting about alternating series, it turns out is all that has to happen to a sub n is they get small. If a sub n heads towards 0 under the limit, then the series converges. It's a pretty simple fact. Now, it's very often and frequent you can get confused that you have such a simple criteria as the terms get small to make a series converge, but it only applies in the alternating series. Now, another part of our proof is going to require our alternating series to be decreasing. However, that is a special part of the one that they're going to prove here. So we're going to add it in here. And a sub n plus 1 is less than or equal to a n. So the terms further out get smaller than each other. It turns out it's helpful in their proof. There's a stronger theorem that doesn't need this. So I'm going to draw a picture of the proof, just as they've done on page 733. And I'm going to point out how nicely these things come together. So let's start at 0 and assume the first term is positive. So we go over this amount to a1. Now, since the next term is negative and smaller than that, we're going to come here, and then we're going to go back a2 to a3. So going down and back. And now we're going to do this again, down and back, with a4 and a5. Why does this represent what's happening? Because length put end to end is summation. So that's a1 plus a2, you're here. a3 plus a4, you're here. a5, you're here. So what's interesting is a1 is an upper bound for all of the odd partial sums. Now the other side is we can do a1, a2, and now we can do this again, a3, a4, a5, a6, and we'll have a lower bound for all of the even partial sums. Well, they have to converge to some value s, because you have the lower partial sum, the odd partial sums bounded above, and we have the even partial sums bounded below. It has to converge to a number s. So it's convergent. Now notice we made use of this. This was very specific in this proof. There's actually a more general one that we can follow. Now, let's take a look at our very first sequence that I was writing down. I wrote down the harmonic sequence. So first off, we know that a sub n equals 1 over n as a series diverges. And that was the proof that we had 1, and then we had a half, And then we had a third and a fourth, which was more than a half again. And then we had a fourth, a fifth, a fifth, a sixth, and a seventh, and an eighth, which was more than a half again. It keeps on adding up in such a way that it's more than a half added on again and again and again. That's why it diverged. But when we make this series with an n or an n plus 1, doesn't matter, over n, this converges because simply a sub n as a limit goes to 0. That's all that's required for the alternating series test. Now that's a pretty simple criteria. So what else should we do with the alternating series? Well, one of the things that we would like to do with the alternating series is we would like to kind of know what might it be adding up to and how accurate can we get that. And so there is one theorem called the alternating series estimate. Now, if you remember, if we write a sum S is the first n terms, we'll call this the head, plus the remaining terms, which you can call the tail. So if you add up enough terms, one would wonder how much is left. And if we get control of that, then we have control of the size of S. Well, it turns out that there is a theorem that says the size of the remainder. Now we put absolute values on it because we now have pluses and minuses involved. But how much of the remaining series is left to be added up? Well, it turns out that that is less than or equal to the very next term in the series, n plus 1. So let's apply that here. Let's start adding up this series. So let's put a plus 1 there so it starts at 1. So this series is 1 minus a half plus a third minus a fourth. And now I'm going to stop there and say I have done S4, and I have the remaining elements to add up. What's this theorem say? Well, it says that the size of S4 is less than or equal to the size of the next term, which is 1/5, or in this case, the most we're going to add or subtract to our first calculation is 0.2. So if we add this up, let's see, this is 0.5 and 1/3, it's 1/12. I can take up my calculator here to get a value on that. So 0.5 plus 1/12. We've got 0.58333. So, well, I don't know if this is addition or a subtraction, so I do 0.5333 plus 0.2. I do 0.5333 minus 0.2, and my sum is somewhere in between there. Now, this is not going to look terribly accurate. It's actually a third up to my sum up to 0.7. So I don't really have a very good idea of the value at the moment of what S is, but I did very minimal calculation. Now, imagine if you did S10. Well, then the size of R10 is less than or equal to 1/11. And so now you know that you have some value S10, and the highest you could go up from there would be 1/11, and the furthest down you can go from there would be 1/11. And so the actual value for S is somewhere between there. Now, there are some very famous alternating series, and I would like to write a couple of them down. We are going to reach the point where we are able to calculate exponentials, sines, logarithms using series. It's our whole reason for doing this. And so I'm going to write down a very well-known series. Now, n factorial simply means start at 1 and keep multiplying until you get up to n. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. Now we do something special. We also declare 0 factorial to be 1, just because we like to use it, and it's a very effective definition. Turns out it is actually natural as well by the time you reach complex variables that you would like 0 factorial to be 1. So if I write this sequence out, it's an alternating sequence. It starts at a plus, so it's going to be a plus 1, minus 1, plus 1, minus 1 over 0 factorial 1, 1 factorial 1, 2 factorial 2, 3 factorial 6. And this is a sequence that takes off like this. Now, this n factorial is a very nice thing to have in your hand, and it's very useful to calculate. What's nice about this factorial is we're going to run into it very, very frequently, so we might as well see it now. Now, turns out this idea of factorial is actually a very big idea. I'm going to graph factorials here. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24. This thing turns, it seems to rise very rapidly. In fact, it does. I'm going to demonstrate, like, pick any number. Let's try 4. I'm going to take powers of 4, I'm going to divide by n factorial, and I'm going to show you what happens after a while. So let's do the first 6 calculations. So 4 times 4 times 4 times 4 times 4 times 4. Suppose I have n is greater than or equal to 6. Because n factorial has as many terms in the bottom as n, 4 to the n in the top, I want you to notice that all of these numbers here I can easily calculate, but from this point on, every time I calculate something, each of those is less than 1. The next one, 4/7. Next one, 4/7. It's very clear that these terms, if this is a sub n, it's going to 0. And that's a very special thing, because if I make an alternating series out of it, I know it's convergent. These are very common series that occur with alternating series. Now, it's easy to spot when you have an alternating series. Why? Well, you have plus or minus powers of n. The next thing is you just have to strip off the negative 1 to some power and determine if what's left gets small. And sometimes it's just very useful to graph. So here, if I write down if this is the series I want to look at, well, I just observe that this is an alternating series, so I ignore that, and I just graph this function. And I ask, does it get small? And when you graph that function, sure enough, it goes to 0, so I know that this converges. It's very quick and easy to look at alternating series, usually, and determine if they converge. There is a few strange things that happen, like we can make some alternating series into telescoping series, but it's uncommon. But we're going to be doing a lot now with series that have negative atoms. So first off, our comparison test, our integral test, I should say tests. Up to this point, we've been assuming positive series. As soon as we entered into the world of plus or minus, so we have alternating series, life gets a little bit more complicated because we don't exactly know what to do with series that are some minuses and some pluses. So let's look at this. Let's say we have 1 plus 2 minus a third minus a fourth plus a fifth plus a sixth minus a seventh minus an eighth, etc. I should have done a 1/2 there. Does this series converge? It's not exactly an alternating series. And what happens if somebody did this? 1 minus a half, then plus a third, plus a fourth, two of them, then minus a fifth, minus a sixth, minus a seventh, minus an eighth, and then plus a ninth, plus a tenth, all the way to, let's see, that was four of them, so five of them, plus 1/14th, and then, so, I mean, there could be a pattern, but it's not alternating. What do we do with these? So it turns out that we're interested in them, and we're going to introduce a few more tests that involve series that simply have some minuses in some form. The alternating series is the most common one, where we have both positives and negatives. All right, that's section on alternating series, section 11.5.